Welcome everyone to this ASB. Today I will guide you through how we can transform traditional CAD workflows into intelligent BIM processes for structures. Uh, Here's what we'll cover today. We will start with a look at industry trends and product strategy, then seamless integration with analysis tools, showing how our solutions connect design and analysis. Then we will move into concrete and rebar detailing, followed by steel detailing and fabrication. And finally, we will wrap up with the design collaboration, where we will talk about how teams can work together more efficiently. Okay, so let's start with industry trends and business strategy. The structural engineering industry is facing big changes. Many firms struggle to find skilled people. Over 50% of them even turn down projects because of labor shortages. At the same time, construction costs are rising, with 30% of costs driven by structural framing, and about 35% of projects still have major design changes happening on site, which is expensive and slows things down. And of course, the sustainability is critical. So steel and concrete alone account for 30% of global emissions. So these trends show why digital transformation is so important for our industry. And BIM is at the center of this transformation. It connects data, people, and processes, allowing continuous improvement and better decisions. By using digital models, we can create, visualize, analyze, and document the buildings more efficiently. So this connected workflow helps all stakeholders collaborate and leads to better project outcomes. So what is our strategy for enabling this process change for structures? Well, our strategy has three main points. I will say first, accelerate digital project delivery by connecting people, processes, and data. Second, optimize processes and deliverables. This means better visualization, coordination, and integration of analytical modeling with detailing and fabrication. And third, enable an open technology ecosystem where Autodesk solutions work seamlessly with partner tools and open standards. So this portfolio shows the solution we offer across the project stages. Revit is the backbone of structural BIM workflows, connecting to analysis tools, detailing software, and partner solutions. Robot structural analysis is our main analysis tool, but we also integrate with partners like Sophistic or Idea Statica. Advanced Steel is still here, but it's in the maintenance mode. We are focusing more on detailing directly in Revit and partner integrations. For collaboration, we use BIM Collaborate Pro and Docs with Navisworks supporting and 3ds Max supporting coordination and visualization. And in construction, Autodesk Construction Cloud ensures data continuity, and in operations, Tandem enables digital twin workflows. So BIM brings real benefits, better data exchange and collaboration, fewer errors and less rework, and optimized use of materials and energy, of course. So for example, firms with high BIM use report 61% improvement in data handovers and 67 better collaboration. They also see a 62 reduction in errors and rework, and nearly half report reductions in material usage and emissions. So the key is having a single digital source of truth that everyone can rely on. So let's move into the product strategy. Uh, what is presented on this slide could be a typical structural flow of users' activities leading to structural outcomes. Some structural analysis to understand buildings' behavior, structural design to determine sizes of elements according to local design codes, structural modeling for construction with cross-disciplinary BIM coordination, and detailing and modeling for fabrication and construction. We are focused on steel and concrete here. So when it comes to amount of data and fidelity collected through these phases, models need to grow from, for instance, LOD 200 to LOD 400. And the reality true is that this is not the sequential process, but a highly iterative one, and that interactions across structural professionals and others are much more complex. Traditionally, these phases were disconnected, so data was lost between steps, leading to rework and errors. And our goal is to solve this by connecting workflows so information moves smoothly from analysis to fabrication without duplication. So these connected workflows are the answer. By linking analysis, design, detailing, and documentation, everyone works with the same data, and this reduces errors, speed up the process, and improves, of course, collaboration between all stakeholders. We have been a leader in digitizing architecture and engineering, and we are currently in the phase of digitalization of construction, but in the real value to the industry and the owners who drive the supply chain is to deliver a digital asset at the end of the project and keep it maintained for their needs for the entirely of its operation. So this digital asset will enable owners to use real-time insight to make a better decision. So we have seen the strategy. Now let's see what CAD to BIM looks like in the practice. So instead of drawing lines, we will model intelligent elements that store data and update automatically across the project. So just like we highlighted before, traditionally a lot of companies worked with 2D drawings, like plans, sections, elevations, and each disciplines work separately, often leading to coordination issues and rework. This slide shows the typical old workflow. So 2D drawings feed analysis models and outputs are manually transferred back, and this process is, slow and error and lacks of collaboration. So some structural engineers enhanced their CAD workflow with structural analysis tool, but these were still disconnected from the drawings. So changes in analysis rarely flowed back into the CAD, leading to duplication of work. And with BIM, we no longer draw lines like in DWG or in some CAD files. Instead, we model real building elements that carry data and information. So architecture, structure, and also MEP are connected in intelligent 3D model, reducing errors and improving design quality. And these modern BIM integrates structural analysis directly with the model. So all the updates are synchronized, saving time and ensuring that structural calculations match the design intent. So when we talk about typical deliverables in structural engineering today, many outputs, just like I like I said, they were still creating in 2D, drawing details and spreadsheets, and these are usually generated from separate tools and often require manual coordination. So any change in one document needs to be updated in multiple places, which increases the risk of errors, of course, and at the same time. And so this approach also makes it harder to maintain a single source of truth across the project team. But this is where BIM changes the game. So instead of working with disconnected 2D documents, we work with an intelligent 3D model that becomes the central hub for all information. So from this one model, we can generate all the same deliverables like drawing, schedules, analysis, data, but with the benefit of full and with the benefit of full coordination. So any change made to the model is automatically reflected everywhere. So this means fewer errors, faster updates, better collaboration between disciplines, of course. So BIM also allows us to visualize and analyze the structure in ways that 2D simply can't, just helping us make better design decisions earlier. So now We have seen how workflows evolve from CAD to BIM, so let's take a closer look at how this transformation impacts specific areas of structural engineering. So we will go step by step through the main domains where BIM makes the biggest difference: design and analysis, detailing for concrete and rebar, steel fabrication, and finally design collaboration across the stakeholders. So now moving to the structural design and analysis. So what users want to see in a BIM-centric solution for structural analysis? Users want analytical modeling in BIM to be accurate and flexible. So they need automation to speed up their work, but also quality control to make sure the model is correct. So the workflows must be driven by engineering needs, not just geometry. So good analytical modeling allows independent control, smooth collaboration, and complete documentation that supports BIM compliance, of course. So this is how the analysis workflow looks today. So first, we can automatically create an analytical model from the physical design. Second, engineers can now take full control over this model, so deciding exactly how it should represent the physical elements. The analytical model is independent, but can stay linked to the physical one for coordination. It's more versatile than before, able to represent any object you need. And third, just like in traditional analysis tools, we can also start directly with the analytical model and use Revit parametric capabilities to define it. And finally, we have a full interoperability analysis. Results come back to Revit when design decisions are captured and ready for detailing downstream. So in Revit, structural engineers can leverage existing physical geometry in 2D and 3D views as context for the analytical model and then decide the physical analytical relationships element by element. The analytical elements are fully parametric and associated with grids and levels, enabling you to control analytical model positioning using these datums and others. When modeling analytical elements, you can assign their structural role, so type and shape, define the cross-section rotation, and specify how these elements should be analyzed. To keep track of the relationships between physical and analytical model elements, you can easily associate them to each other. When this is done, associated elements can be easily located within the model, and this association can be utilized for automating synchronization of properties between physical and analytical models. It's also worth mentioning is that structural engineers can associate multiple analytical panels or members to a single physical object. For example, several analytical panels used to represent a single physical floor, several beams associated to a single multi-span analytical member, etc. So the analytical model can be associated to physical geometry, but at the same time, it remains independent, providing you with the benefits of speed and accuracy in model creation and editing while protecting the analytical model from unexpected changes. And Revit provides engineers with a diverse range of tools for editing an analytical model, greatly enhancing the efficiency of the model creation process. So you can, for instance, perform tasks such as splitting, extending, trimming elements, and much more. With the modeling autonomy enabled by member and panel objects, the analytical model can represent not just Revit structural elements, but also generic objects. No, for instance, roof structures, some stairs, compound geometries, etc. And Revit also provides structural engineers the rule-based structural analytical model automation. So this tool enables you to generate, for instance, a structural analytical model automatically from selected physical geometry. So this solution ensures that the automatically created model is always consistent and connected. So we are eliminating the need for do some manual correction and corrections and rework. And as the analytical model is completely autonomous, it allows structural engineers to initiate structural analysis workflows from Revit without any physical geometry. Instead, they can start a new model from scratch and focus exclusively on aspects of analysis. So engineers can start modeling with analytical geometry and simply add some physical geometry when needed for the construction, documentation, and detailing phases. So this workflow is especially well suited and applicable to projects where engineering requirements dictate the design. And of course, it depends, depending on the load duration and type, different natures of loads can be created. So then various types of loads such as point, linear, planar loads can be applied to a structured assigned to previously defined load cases. So these loads can be easily and accurately applied to specific areas of panels, and members are copied to uh, another physical another analytical host for instance. Hosted loads apply to specific areas of panels and members. Point loads can be placed anywhere on their host, and loads can be constrained to their host's boundaries. So this is in general a couple of informations about structural loads. And Revit's unleashed versatility for defining analytical model geometry enables true bi-directional analysis software workflows and capturing edits made in other tools while eliminating modeling limitations. This BIM-centric approach to structural analytical modeling offers many benefits to structural engineers, so you can more easily create representations for any type of structure, buildings, bridges, frames, pavilions, stairs, and more. So you can create some consistent analytical models that align with their preferred engineering approach. And you can of course, enable structural analysis jobs from Revit models. So you can even create a multiple analytical model for a single physical representation and consider various analysis approach simultaneously. So this is that there are several ways. And yes, structural engineers can also work on both types of models concurrently. So this has the potential to save a lot of time, and they enter the model data only once. So once robot structural analysis professionally is installed, Revit add-ins command to send the entire model or selected parts for analysis and design, update the model with results, or use an intermediate file for data transfer. This is for the cases without analysis results when robot is in another machine, for instance. And element mapping ensures correct profile recognition and all selected analytical elements, load cases, and the load transfers seamlessly to robot. And after transferring the analytical model from Revit to Robot, the engineer must review and adjust model parameters, cross-sections, slab types, and local coordinate systems before analysis, of course. The display dialogs helps toggle nodes, loads, supports, and finished element mesh for verification, while tables allow quick parameter adjustments. So engineers can redefine temporary sections, set correct thickness, and align orthography direction, ensuring the robot model accurately reflects the design intent, of course. During a project, engineers must account to wind effects, which are typically defined in Robot rather than Revit due to its advanced wind load generation tool. Robot wind load simulation acts like a virtual wind tunnel, allowing airflow simulation, automatic wind load generation, and visualization of pressure maps, especially for complex geometries. So engineers can specify wind parameters, exposed elements, and profile with load cases created for each wind direction. Robot also supports manual or automatic creation of load combinations based on building codes, ensuring structures safely resist various loading scenarios. After modeling the structure and the defining boundary condition to loads, the engineer generates a finite element mesh, verifies the model, and runs the analysis. The robot allows custom meshing per panel for detailed results in specific areas, and others mesh freeze to avoid remeshing on every calculation, saving time. It supports various analysis types: linear, nonlinear, seismic, modal, time history, and more, covering most project needs. When calculations finish, robot confirms results are ready for review and all load combinations. Once a structural analysis has been completed in robot structural analysis, results may be viewed for specific elements, parts of the structure, or the entire structure. Many different options are available to access, present, and review these results, enabling structural engineers to quickly document their designs for review and input by project stakeholders. Diagrams of structural deformation and selected forces on structural members may be displayed. Results may also be presented as we can see, as some colorful maps of displacements, moments, and stress obtained during the structural analysis, providing a visual snapshot of a structure's behavior. So these features offer structural engineers some immediate access to analyze these results, while also helping make robot intuitive and easy to use. Building elements must resist loads defined by building codes, of course, and this is the engineer's responsibility to ensure compliance. So robot structural analysis verifies and designs steel, concrete, and timber elements per international standards, optimizing sections and materials to meet code requirements efficiently. Engineers group members like beams, columns, braces for design, apply optimized sections, and rerun analysis as properties change. So this iterative process ensures code compliance, with robot also providing tools to generate final structural documentation. And yeah, after completing analysis and design in Robot, the results can be imported back into the Revit, allowing designers to review changes and update the physical model accordingly. So results can be visualized in Revit using the Results Explorer as maps or diagrams, helping engineers understand structural behavior and make informed design decisions. This bi-directional link between Revit and robots stimulates workflows and integrates structural analysis directly into the BIM process. So yeah, our structural strategy has been focused on enabling BIM workflows through platforms and to be inclusive to the ecosystem of partners. So partners connect and integrate their mature and specialized technologies with Revit, bringing more productivity, specialization, region-specific compliance, and much more value overall. So in this workflow, we see how structural analysis and design integrate with the BIM process. While robot structural analysis is a powerful tool with the Autodesk ecosystem, this is not only the option. So maybe so many engineers use other analyzers like CR, ITABS, or Nexus or something different. So the key point is that Revit is not locked into the single analysis engine. Thanks to open standards and our data exchange capabilities, we can share and update subsets of data across platforms. And with data exchange, we can transfer only the relevant parts of the model. For example, just structural members of specific load cases to another analysis or detailing platform, and bring the results back. So this avoids exporting entire, for instance, IFC models unnecessarily and keeps the workflow efficient. So for example, you can send data from Revit to another analysis software or to Tekla, or from Tekla back to Revit using the connectors. These connectors allows us to keep models in sync without some overwriting everything, ensuring a smooth collaboration. So instead of think about this is a Revit plus robot pipeline only, think of it as an open, flexible data flow between multiple solutions with Revit at the center of the coordination, of course. Okay, and in this session, we will focus on how Revit enhance concrete and rebar detailing. These workflows combine structural modeling, analysis, code-based design, and detail reinforce modeling. The reinforcement is smart. It adapts to host elements in Revit and keeps information for scheduling and documentation. So with these, engineers and detailers can work in one environment and minimizing mistakes. Revit offers multiple rebar placement methods, planar, multiplanar, and freeform, so giving engineers full flexibility to match real-world reinforcement. The shape, hooks, diameters, and other parameters are fully customizable. This makes it possible to accurately model even complex reinforcement layouts. Rebar segments can be edited directly in the canvas with intuitive controls to adjust lengths, hooks, and spaces as well. Each bar type has parameters like diameter, bend radius, hook dimensions, and material, which are fully customizable. And these parameters are stored as a data, so not just graphics, so they can be scheduled, tagged, and used in fabrication. Rebar shapes in Revit help quickly define how reinforcement will look and behave. So they allow you to pick from standard stirrups or ties, or create custom ones with exact dimensions. So the geometry can be easily controlled, edited, and reused. Each shape stores data like bend radius, hook lengths, and bar diameter, so schedules and fabrication drawings stay accurate without extra work. And yeah, rebar hooks are fully parametric as well, which means every aspect, just like I mentioned, diameter, bar length, and angles can be adjusted to meet design code and requirements. Rebar needs a host element where it is placed, and Revit supports many options. So you can reinforce structural framing, columns, foundations, floors, walls, etc. Even more complex elements like in-place stairs, freeform geometry, and generic models can host rebar as well. In Revit, covers can be set for each face of an element, top, bottom, sides, or interior and exterior faces of walls. Different cover settings can be assigned depending on exposure conditions or design needs, and they automatically control the rebel placement distance from the surface. Placing planetary bar in Revit is straightforward and works from any 2D view, so plan, section, or elevation. You can choose the placement method, define the plane where the rebar lies, and set its orientation relative to the host. The shape browser lets you pick the right bar type instantly, so these options make it easy to place reinforcement exactly where needed, keeping it aligned with design intent and cover requirements as well. And yeah, this is just an example showing how placement references control exactly where the rebar sits. Sketching planar rebar. allows you to create reinforcement exactly as you need it. So you can draw it from scratch or copy an existing shape and adjust it. The sketch automatically matches an existing shape definition or create a new one if it's unique. So you can control every segment, hook direction, and bend dimensions. Because it's editable family, any custom shape can be saved and reused, of course, for speeding up for future detailing. And yeah, we have also some intuitive editing of rebar segment lengths, which makes detailing faster. So you can directly click and adjust dimensions in the canvas, and the start point stays fixed while the segment resizes. So dimensions automatically display in 2D and 3D views, matching the shape family definition. So this live editing is as simple as typing values in the properties, but much quicker and more visual. Rebar sets make placing multiple bars easily and flexible, so you can define them with a fixed number where spacing adjusts automatically, or with maximum spacing where the bar count adapts. If you need some constant values, use a number with spacing, and when clearances are critical, minimum clear spaces ensures code compliant gaps. So these options help model reinforcement quickly while staying accurate to design and standards. And here is a video where you can see it in some sample. Varying rebar sets are designed for elements with included or screwed faces where bar length needs to change gradually. This is also possible to very easily model in a Revit, so each bar adapts to the geometry based on constraints, while only the first bar parameters are shown directly in the properties. This approach is perfect for ramps, some slope beams, or some tapered walls as well. Flipping a rebar set is a quick way to change the direction in which the bars expand without recreating them. This feature works with the number with spacing layout and helps adjust bar orientation instantly for detailing. And again, this is just an example of adaptive propagation for rebar. We will skip this video because we are running of the time of this video, so you can check it in PowerPoint presentation and watch it later. The parametric rebar splicing is one of the most important productivity tools for concrete detailing, recently added to the Revit. So now you can split one or several rebar sets at the selected position. Uh, Here we have some time, so we can show it in this video. So you can split them by length and modify the splices as needed. This feature significantly improves your efficiency and productivity in modeling accurate reinforcement of concrete structures. Next, speaking about enhanced rebar set representation, you can also set up the presentation options for multiple rebar set at once. So thanks to this capability, you can create also reinforcement floor plans more easily by managing the presentation options of multiple rebar sets in once. And you can also easily visually inspect bars that require length adjustments. So using Revit filters, you can highlight bars that exceed the maximum length and require splicing. Rebar in path reinforcement have the same length but are not parallel to each other. So the rebar is perpendicular to boundary you specify. So we can use also some common sketch tools to sketch a path populated by a system of rebar. Revit also places a path reinforcement symbol and the path reinforcement tag on the completed sketch at the center of the longest segment of the path. And so these tools simplify reinforcement for walls and floors. We have also area reinforcement, which automatically distributes bars with across the surface uh, while pattern reinforcement lets you define bars along edges of openings. We have also fabric areas, and sheets can be applied to represent mesh reinforcement, and together they speed up modeling while keeping detailing accurate and consistent with real construction practices. And then we have also a wire fabric reinforcement, which is ideal for slabs where mesh seats need to be applied quickly. In Revit, you can define fabric areas, place predefined sheets, and automatically generate schedules listing sheet types, weights, and quantities. This is not only speeds up detailing, but also ensures fabrication data is accurate and ready to use on site. Then we have a freeform rebar, which freeform rebar with surface distribution is perfect for some irregular or curved elements. Bars are placed by selecting host, start, and end faces with interpolation filling the space between the first and the last bar. This method works well on complex surfaces, but it's a powerful tool for modeling reinforcement in non-standard geometries. And yet, this freeform rebar also supports distribution along multiple surfaces, so giving us more control over how bars follow complex shapes. And again, this method is great for circular or some radius layouts where bars needs to follow a curve while staying evenly aligned. So these bars can be also connected with couplers and match an existing geometry. Users can choose also how to align the bars in the rebar set. Also, you can make the bars in the set to be parallel to the planar face selected in the align close constraint. So you can set the alignment options for freeform rebar sets using bar alignment parameter in the properties palette of the structural rebar, or using the in canvas toggle. And here we can also, this is just a video where we can see the demonstration of these functionalities. Again, we want that this video will not be super long, so for this example, I will skip this video. Then we have couplers in Revit, which let us model mechanical connections between rebar segments. They are customizable families, so you can it can be applied to single bars or sets and work in groups or assemblies, of course. So each coupler gets a unique number, supports end treatments, and it can be tagged in drawings. So again, this ensures clear documentation and let's say some accurate fabrication of split reinforcement. Then we have reinforcement partitioning. So rebar and fabric reinforcement have a number sequencing that matches with existing reinforcements, and numbering allows identical reinforcement elements to be matched for schedules and tags, of course. So in assigned partitions, the rebar and fabric sheet numbers match those of the same type, size, material, and shapes, and the number for a rebar or fabric sheet instance may be viewed in the properties palette under identity data. And yeah, we have also a dialog for setting up a reinforcement rounding, which allows us to set some numerical rounding of rebar lengths to simplify organization and annotation when tagging, filtering, or scheduling rebar. So again, these rounding values defined in the reinforcement settings dialog and propagated to the rebar type properties and the rebar instance properties dialog. So rebar length displayed in the properties palette uh, displays in dual format, exact length and rounded length in the brackets. So you can manually override these values for the bar type and the bar instance by editing the exact length properties if needed. Tagging is also essential for clear and accurate documentation because it links model elements directly to their data. Tags automatically read parameters from the model, so any change in geometry or properties updates the drawings instantly. So in Revit, we can tag multiple rebars with one leader, control or with multiple leaders, control the visibility of leaders, and adjust from individually of all at once, making annotation fast and reliable. And of course, we have multi-rebar annotation, which allows us to tag multiple rebar and rebar sets with a single annotation. So we can use this multi-rebar annotation to tag each bar in a rebar set with a detailed annotation for fabrication and construction. And yeah, these are another examples of multi-rebar annotations here in these slides. And we can also check the behavior and the functionality about multi-rebar annotation on this video. You can check it on this video sample. Then we have automatic tag placement for multi-rebar annotations, which again speeds up the documentation process by aligning tags with just 2 clicks, and tags position automatically on dimension lines, adapting whether you click inside or outside the reference area. So with the pick position toggle, you can choose between manual control of fully automated placement, making coordination between design and fabrication again much more efficient. So yeah, we can place multi-rebar annotation with just 2 clicks. Tag position when clicking inside the dimension light, time position when clicking outside dimension light, and toggle pick position of the automatic tag placement behavior. And then we have, of course, schedules. An important part of reinforcement schedules and bar lists are the bending details. These details clearly describe each bar's shape, dimensions, and bending angles. So it also ensures that fabrication and installation follow the design exactly, including accurate bending details help meet standard documentation practices and improves, of course, coordination between designers and fabricators. Rebar schedules also include bending details directly inside the table. So small uh, these small graphical representations show the exact shape of each bar and its dimensions, making it easy for fabrication and understand the requirements at the glance. The details are scaled automatically to fit the schedule cells, keeping the documentation clear and standardized. Yep. And in this example, to make the drawings easier to read, we can also move the dimensions and text. They are automatically placed with the bending details on the drawings, eliminating text some overlaps with just a few clicks. And these new features, for bending details, streamlines the coordination between designers and fabricators by improving the clarity of shop drawings in Revit. So yeah, here we bring everything together into a final shop drawing. So these drawings combine 3D reinforcement models if needed, bars, schedules, and bending details into a clear fabrication-ready sheet. In this video, you can see how the views, section, and schedules are arranged and automatically updated when the model changes. This workflow ensures that every drawing stays consistent with the latest design, minimizing errors and saving the time during detailing. Again, it depends on us how it will be the visual of the sheet. Again, in this example, it is just an example of another visual of a multi-rebar annotation about tagging. Again, it depends on the location, depends on the national standards. So this is also possible to modify and prepare the families, the tags, the annotation in Revit as well. And yeah, we constantly refer to Revit as a BIM platform, and so it is the case for rebar. We know the industry practices are all around the world, and how each firm has its own workflow. Therefore, we work with our technology partners from CAD, Greatex, Sophistic, and Symmetry to deliver custom rebar detailing solutions, as well as code-driven rebar generation according to various local codes, which is the case for Sophistic and Greatec. And for precast concrete, we follow a similar philosophy. So the customization plays here an even greater role. So from the types of chamfers to the way the shop drawings needs to look like, and to what information needs to be written in the CAM files. Everything can be personalized by our tech partners from AJK that progresses as well. Okay, and I would like to show you our vision and strategy for structural steel and where we are investing in product development. So to set the stage, I would like to share our vision. So this vision really informs how we invest in our products and which way we develop them. So where are we now? Advanced steel is still available and supported, but it's now in maintenance mode. So you can use it to model steel parts and create drawings and CNC files. Revit focuses on steel design and collaboration. It supports analytical models for analysis, physical models for coordination, and design documentation. We are now putting our efforts into Revit to make it a full design to fabrication solution. So here we combine several Autodesk tools in one workflow. First, in Revit, we model a structural frame and set up the basic elements. Then we use robot structural analysis to calculate the forces and moments, and we are bringing those results back into to the Revit. We can use also Dynamo. We automate the placement of connections based on the rules and predefined ranges. And finally, Revit generates the steel connections directly in the model, ready for detailing and documentation. So this way, Autodesk covers the entire process from design to analysis to automated detailing. So you can model your design intent faster while embedding engineering and fabrication rules to reduce iterations. Sample rules for placing steel connections based on ranges are applicability and available in the steel connection automation player. Just search for instance, by ranges. Structural members can use analytical data of imported analysis results from robot structural analysis or other tools. And connections are placed according to criteria like profile sizes, steel grades, and internal forces using predefined libraries with geometry parameters and ranges. And Revit provides sample libraries that you can customize to meet local standards, enabling quicker and more accurate steel design. In this slide, we show how the automation of steel connections works and an end-to-end workflows. You start with structural modeling in Revit. You use robot structural analysis to calculate internal forces and feed those results into library-based design using Dynamo. And finally, all data pushed back into Revit to automatically generate detailed steel connections based on analysis and predefined the rules. So structural engineers use Autodesk Revit to design these steel structures with built-in steel families and a library of right now more than 125 parametric connections. Connections can be inserted by selecting members and choosing from the drop-down menu which parameters adjustable in the properties dialog. Revit lets us create and save custom connection libraries as well, so we can automate placement using sizing rules and use tools like copy or propagate to speed up modeling. This result is highly detailed, accurate models that link steel design with steel detailing. And yeah, structural engineers and steel detailers can link then Revit to advanced steel to work on the same 3D model, saving time and reducing errors. The advanced steel extension for Revit allows easy BIM data exchange. So after installing it from your Autodesk account, you have to restart Revit and you will find it under add-ins. So you can export the model as an SMLX file, which options to export the entire model or only selected elements. And then in advanced steel, we can import the file to keep parametric connections and data, then run automatic numbering and generate fabrication drawings quickly. So last but not least, I would like to remind you that we are a platform solution company. So we are building products that can be further customized through our partners' offerings. So Grating and Manameshing are our partners in providing support and further customization in our Autodesk products. Also, we have partners that provide solutions for Japanese market, automated connections, and fabrication deliverables out of Revit. And finally, we also have solutions for not only for steel but also for timber and cross-laminated timber. So with our partners, Greatech, AGCAD, HSB, CAD, they build their solutions on top of Revit, so you can really streamline your design, detailing, and fabrication process. Also, when the topic will be about speaking about timber. Yeah, so let's move into design collaboration, then documenting design intent, creating engineering drawings, modeling for construction, coordinating across disciplines. This is where Revit has gained in its reputation. There are also some important workflow advancements you can see, you will be able to see here being developed there that help engineers coordinate while authoring. So modeling and documenting, they are BIM models in Revit. So for instance, in this workflow, we start by modeling and detailing the structure in Revit. The model is then checked using clash detection in Construction Cloud, where any where any conflicts are automatically identified. Detached clashes are reported as issues, assigned to the right people, and tracked until resolved. And finally, the structural team fixes the clashes directly in the model, ensuring it's coordinated and ready for them for the next stage. So here's the demonstration how this BIM allows smooth coordination between different disciplines. So as we can see, the structural model is linked with architectural and MEP models, and Autodesk Construction Cloud continuously checks for conflicts. And yeah, issues are flagged early, discussed, and resolved before they reach the construction phase. So this process avoids costly errors and keeps the projects on schedule. And in this workflow, this workflow is focused especially on the rebar. So reinforcement is modeled in detail in Revit, then checked for clashes both internally and against other elements, and any detected problems are documented and assigned through Autodesk Construction Cloud issue tracking. So once corrections are made, the model is clash free and fabrication ready. And here is another video sample. So in this demo, we can see how we upload both the structural and rebar models into Construction Cloud. Once the models are in the cloud, we can simply enable the clash detection. The system automatically scans and highlights all conflicts between reinforcement, concrete, and other building elements. What's great is that clashes are not only detected but also, as we can see, automatically turned into issues right at those locations. So each issue contains all the context, where it is, what's wrong, who should fix it, etc. So using this issue tracking, we can quickly assign responsibilities, follow up on progress, and close the issue once it's resolved. This makes just coordination much faster and ensures that reinforcement and embedded elements do not interfere with openings or reserved spaces, and everything is detected early. It's fixed earlier and tracked through one streamlined process as well. So yeah, we will move into the roadmaps and closing. I highly recommend this structural analysis roadmap. We also prepared a link. You can see QR code on the top right of the screen. Where you will find much more information we are preparing and where we want to go. So yeah, that was all about this ASB. So I'm happy to answer if you have any questions.